Hello everyone and welcome back. This week's topic is cryptographic hash functions. So I'm planning to divide this talk into three parts. First, I will talk about what a cryptographic hash function is and how we can construct them. I will also talk how we can construct a hash function from a block cipher. Then we will talk about dedicated functions like MD4, MD5, SHA-1, SHA-2. Then I will move on to SHA-3 competition, and the winner was Ketchak algorithm. So we will talk about SHA-3 algorithm at the end. So let's start. So let's start with the definition of a hash function. A function h is a keyless algorithm that takes a variable length input x and returns an output y of fixed length n, and we call this n message digest length. So idea is simple. We are trying to design an algorithm which can take a variable length input, but the output size is always fixed. So from a very huge space, like an infinitely large space, we are always giving small output. So this means that there will be collisions at the end. So of course you can design this kind of functions easily, but in order for a hash function to be called a cryptographic hash function, it has to satisfy a few properties. The following three properties are required for security. So we expect the cryptographic hash function to satisfy the following properties: pre-image resistance, second pre-image resistance, and collision resistance. So I will mention all of them in the following slides. But at the end, what we are requiring is actually, so what we really want is that a hash function to behave like a random function. So let's start with these three resistance definitions and see why we require them, because you can easily design a hash function and sometimes you use them for as a compression function, and maybe you can use them a general hash function in a database to gain from the storage. But cryptographic hash functions can be used in many different ways. We will see examples in a minute, but let's see why the properties we require and give a few examples to see why we require such properties. So the first property we require is pre-image resistance. So given an output y, it should be hard to find any input x such that hx equals to y. So you are given an algorithm h, this is a hash function, and you're also given an output, and you're asked to find an input that gives this output. So we're saying that for a hash function, it should be hard to find such an x. So in other words, we want this function to be one way. So of course, saying it should be hard is not scientific, but we are trying to give the main idea. So hash function to be pre-image resistant, there shouldn't be any easy way to find such an x, and you can always, of course, apply brute force attacks. Namely, you can try a lot of x's as an input and try to check if the output is y. And since the y is of n bits, probabilistically speaking, it should be enough for you to try 2 to the n different x inputs, and your expected value becomes 1 after the 2 to the n operations. So we are expected to obtain one input that gives this output in a brute force attacks. So of course, if there are weaknesses in your hash function, you can find faster attacks than brute force attacks. And we will see some examples. For instance, MD4, MD5, or SHA-1 can be broken faster than this generic attack. So here's a basic example why we need such a property. Assume that you are storing usernames and passwords, and almost every web page now does this, and a lot of application does this. So we are requiring people to choose a username and password and use them for logging into the system. So you have to store this information in order to check if the person who provides the password matches with the one you have. So you can, in your database, you can create a table, and in one column you can store the username, and in the next one you can store the password. And this is the worst thing you can do. And a lot of web pages in early years of internet, but still today does this, which is a really bad idea, because almost every database leaks at least once in their lifetime. So if you keep this like a plain text like this, then if the database leaks, then every username and password also leaks. So people capture other people's accounts. So basic way to avoid this, instead of storing the password, just apply the h function here. So take the hash of it and store the hash instead. So whenever somebody tries to log into your system, they will provide you the password. You would compute the hash of it and check in your database if this hash matches with the one you have. So if it matches, then you will allow them to log into system. So this is sufficient to verify a password. But the good thing is, if the database leaks, what leaks is that every username and the hash of every password, if it is premise resistant, then the person who captures this database would not be able to capture the passwords. So this was the basic idea cryptographers suggested maybe more than 20 or 30 years ago, but people still don't use that. We have a lot of examples, but of course I don't want to give them, because this way I will be showing hackers to a place to attack. But even in this example, I'm actually showing you how to do it basically. Even this approach is not a good idea, because people choose easy passwords. So now you can try. In this way, you can perform brute force attacks again by trying every short password, or you can perform dictionary attacks, which means that you can store the hash of a lot of passwords and check if those hashes which you pre-computed matches this one. So this is just an example. In the following week, when we will be talking about password cracking, I will mention you how to actually store your passwords. But to give the gist of it, you have to extend this password. So you should concatenate a random value, which we will be calling salt, and take the hash of it just not once, but maybe 10,000 times. Okay, so this is just an example. Just don't also use it in this way. But even again, this is better than not storing it like this. So never do this. And if you are doing this, I'm saying that you can do better. So long story short, an attacker that captures the password file has to find the pre-image. So if the hash function is pre-image resistant, then they cannot. So this is a good thing. Of course, this is just a one application. There, I can give you 100 examples where you need a hash function to be pre-image resistant, but we will see examples throughout the course. So let's move on to the second property. Second thing we require for a hash function to be a cryptographic hash function is the second pre-image resistance. Given an output y and input x1 such that hx1 equals to y, it should be hard to find any other input x2 such that hx2 still gives you the same output y. So in this picture now, you have an input x1, you know it, and you can also compute the hash of it, so you know the y2. So you are given x1 and a hash function and y. Now we are asking you to find another input which is different than x1, but still gives you the same output. So theoretically speaking, this is always possible, because as we have, it comes from the definition from the hash function, because the output size y is fixed. For instance, maybe it's just 16 bytes, but as an input you can give anything like from 5 bits to 100 gigabytes. So the input space is really large, but the output space is just a very small compared to it, but it is also still large, because y can take 2 to the n different values. It is still virtually infinite to us, but when compared to the input space, it is really small. So you can always find such an input x2, but we are requiring it to be hash function to be secure against second pre-image resistance attacks, so that other than brute force attacks, there shouldn't be any way to find such an x2. And if you perform a brute force attacks, again, you have to try around 2 to the n different x2 values and check if it provides you y. And around this many operations, you will find such an input if you perform a brute force attack. So why we need such a thing? So assume that you store the hashes of your files because you want to check if any of the files are changed in the future. So assume that you calculate the hashes of all of your files and you store them. And later on, a virus or somebody just modified one of your files. When you do that, this modified file, assume that your file is x1, so you store the hash y. So they modified your file, now it became h2. If it is second premise resistant, then the output would never be y. But if it is a weak hash function, and people does these modifications, but of course, changing one bit would definitely will give some different value. But adding some things more, maybe they can still provide y if it is not second premise resistant. So if the attacker modifies the files, for example, if they put a malicious code inside them and can still obtain the same hash value, then the attacker can fool you. So this is the main idea, and actually this is important for forensics. At the crime scene or any investigation, you have to take the hash of the hard drive, but I always suggest to take the hashes of every file on the system, actually for many reasons, but we don't have time to discuss all of them. So this is important because I can give a lot of other examples to assume that you signed something electronically saying that I'm transferring $10 to this person, but if they change this $10 to $10,000, and if it still gives the same hash value, they may claim that you signed that message instead. So instead of $10, they may ask you to pay them $10,000 and so on. So let's move on to the last property that we call the collision resistance. So it should be hard to find two inputs, xy and x2, such that hx1 equals to hx2, which equals to some value y. So it might look like the previous property. It is almost the same, but there is one difference. If you go back to the previous picture, you were given x1. So x1 was fixed. You don't have any control over x1. Assume that it is a file in your computer, or at the forensics level, it is the hash of the hard drive, so you don't have any control of it. So the hash value is fixed. So you are trying to find some other x2. So x1 is fixed, you are searching for an x2. But in this picture, in the third property, nothing is fixed. So you are only given the hash function h, and we are asking you if you can find two different inputs that would give you the same output. So as you can see, you have more freedom here now because x1 is not fixed. So you can do whatever you want. And a generic attack would require around 2 to the n over 2 operations due to the birthday paradox. As you can see, until now, I always said that brute force attack would require around 2 to the n operations. And now I'm saying that it is a lot easier because this is the square root of 2 to the n. So this number is really small compared to the others. It is not just by division by 2, but it is the division of the power n. So if for instance n is 128 bits, previous attack requires 2 to the 128 operations, but for a collision resistance you need 2 to the 64 operations, which is really small compared to the 2 to the 128. So this comes from birthday paradox. I will explain it to you in a minute, but let's see why we need such a property. A simple example is as follows. Assume that as a hacker, somebody prepares two versions of a software driver for an operating system where x1 is correct and x2 contains a backdoor, but they're still the same software driver. And that backdoor allows the access to the machine or some other, any kind of malware you can imagine, maybe a ransomware. So if they can achieve this and say obtain still, if they still provide the same hash value, what they will do is as follows. Hacker sends x1 to the operating system company for inspection. So they will check it and will not find anything malicious, and they will sign it. They will sign the software driver, but when we'll see in public key cryptography, signing a message or a huge file is not something practical. Imagine the current drivers, for instance, GPU drivers are now sometimes 1 or 2 gigabytes. So signing a 2 gigabyte file would be impractical. So instead of signing a 2 gigabytes software driver, you sign the hash of it, which is like 160 bits or 256 bits, which is just, a few bytes. So operating system company signs the hash of the driver, HX1, but now hacker distributes X2, which has the malicious code inside, and they distribute to the users. Probably they put in their web page or so. And when the users try to install this driver, their operating system will try to verify this driver. So they will take the hash of this driver and check if the signature matches. But since HX1 equals to HX2, and the operating system signed this hash, this means that they also signed this too. So when you're trying to install, you will be trying to installing this driver, the operating system will think that, okay, I already checked this driver and it was secure. So it will say to the user that you can install this driver. We didn't find anything malicious in it, but actually there was a malicious code inside. So collision resistance can be used in this way, but of course it can be, if the hash function is not collision resistant, the attacker can use this in some other types of attacks. For instance, if you know the hash of a file in a cloud system, but you don't know the file, but if you can find another file with the same hash value, you can trick the cloud and claim that you have that file, and you can access that file from the cloud, and so on. So let's talk about birthday paradox and finish this video. So birthday paradox is as follows. Question is this: how many people need to be in a room before it is more likely than not at least 2 people share a birthday with probability 1/2? So you're putting people inside the room, and at which point there will be 2 people in the room with the same birthday with probability more than 1/2. So we can compute this as follows. So consider the probability that nobody shares a birthday. How can this happen? When the first person goes inside the room, so they can have any birthday, because since there's a single person in the room, there won't be any collision. So with probability 1, there won't be any 2 people in the room with the same birthday. But when you get the second person in the room, so there are only 364 days left in the year, so that the first person and the second person don't have the same birthday. So probability of this is 364 divided by 365, which is the number of days in a year. So when the third person goes inside the room, so they should have a different birthday from the first 2 people. So the probability of this happening is this, and so on and so forth. So if you write this, it will be the summation. So question is, after which point this probability would be less than 1/2? And if you think the other way around, so the probability P that we have at least 1 match is 1 minus the previous summation, which is this. So question is, what should I choose T so that this number becomes more than 1/2, so 0.5. The answer is 23. So when there's, if you do this multiplication, sorry, I said summation, but it was obviously a multiplication, sorry. So after the 23rd person enters the room, the probability becomes 0.507, which is more than 0.5. So if there are a few more people in the room, then this probability really increases. So you can try this if there are more than like 30 people in the room, and you will observe that you can find 2 people with the same birthday. So actually there is nothing mysterious here, but you might think that why it is called a paradox, because when this question is asked, people think that the answer would be more than 100 or something. But when the answer is really small, like 23, compared to the number of days in a year, which is 365, People thought that this was a paradox, but if you do the computation like here, it is not a paradox. But of course, what does this say for our hash collisions? For the more general case where we have t people and n possible birthdays, it can be shown that the probability is approximated like this. So when there are n possibilities, after making approximately t equals the square root of n choices, we have a collision with probability more than 1/2. So this means that here n is the number of bits of our hash output. So if you try t different input, so start from x1, x2, go until xt, and store all of the hashes. And when you look at them, there will be two hashes in this table, same hashes with probability more than 1/2. So this is how it affects our collision finding in hashes. So this is why a brute force attack requires 2 to the n/2 operations to find a collision.